Switching is one of the important topic. The reason why is if you take an office, if you take an enterprises, if you take an organization, they have many end devices and host, computers, iPhones, IP phones, IP printers, IP scanner, IP cameras, all right, servers. So, and many departments. Now, when we take a department, in a department you will have some dedicated printers, some computers, some servers. Now, to combine all these devices, to connect to all the devices of each department needs a switch. They don't need a router because they're all in the same subnet. Each department will be in one network, same network. So they need a smart device which can move the packet among themselves faster with no loops. No one likes loop. What is the problem with loop? Loop will block the traffic. Loop will consume bandwidth. Loop will never allow the packet to reach the original destination. So loop is an unacceptable one in networking. No one likes loop. So we need a device which will smartly prevent loop, which will smartly move the packet to the right destination without any confusion, which will do unicast instead of always broadcast. For that, we need a smart device. The smart device is a switch. Because we learned earlier, switches listen to the incoming frame in order to learn the source MAC of the connected device. Very first smart behavior of a switch, listen. They are listening. They listen. Say, listening is not only for switches. Even for us, listening is very important if we want to learn. Otherwise, no learning without listening. No possibility of learning without listening. Switches listen, hub don't listen. Even router listens. So that's why router is a smart device, switch is a smart device. Anything that listens is a smart device. All those people who don't listen in schools, they never finish the school. Sometimes they luckily finish, but they never finish the degree. So listening makes smart. Someone makes someone smart. So in here, switch listens to the what? Incoming frame. In the frame, you will see a source MAC address and destination MAC address. And the source MAC address is now learned in a table called MAC table. So we got some computers. I have already drawn this diagram when we were learning devices. So it's a known story for us. We got port number 1, let's say fast Ethernet 0/0. What does that 0/0 means? In Cisco devices, the naming convention is like this. The line card, the first line card in which you have ports, they are called as slot 0. If you have another line card, another row of ports, that is slot 1. Now, F0/0 means this one. 0th slot, 0th port. In first slot, first port is what here, 0th slot, 0 port. So let's say yes. Now, what is the difference between Ethernet and fast Ethernet? F is fast Ethernet. Ethernet is E is Ethernet. This is fast Ethernet. Fast Ethernet is 100 meg speed. Ethernet is 10 meg speed. If you have gig Ethernet, gig Ethernet, there's no A there, Ethernet. If you have gig Ethernet, then it is 1000 meg speed. 10 gig is 10,000. Just like that. Yeah, megabits per second, bits per second. So the speed and the name. Fast Ethernet 100 meg fixed. If you want to reduce it, you can reduce it, but you can't increase. If you want to reduce it, you may go to the interface and say speed 50 meg. Now we got fast Ethernet 00 only on the router. On the switches, you will not find 00. Switches will always start with 1. There is no 0th port. They call first port. Slot 0, first port. And then F0/2. F0/3. F0/4. This is how the names are given. Now let us assume the MAC address. We learned already MAC address is 48-bit size. Instead of writing that 48-bit, I'm writing simply AAA, BB, C6, DD. Now let us assume A is trying to talk to D. A wants to talk to D. The frame is sourced with AAA. The destination is DDD. When the packet approaches this port F00, immediately the first thing the switch will do is learn the source MAC address from this incoming frame. So it learns in a MAC table saying on F0/1 we got A connected. Now the destination DDD is not available. When the destination is unknown in the table, only when the destination is unavailable switches will broadcast. So that is also a smart move, It's not denying, saying, I don't know, I will not send. It says, okay, because I don't know, let me send it to every port, and one of the port may have the destination. So switches will broadcast only if destination is unknown. Destination is unknown. Only when the destination is unknown, it will broadcast. Now, after the broadcast, the packet manages to go to D. It is not only going to D, it also goes to B and C. They reject the packet because the destination MAC address is not matching with their own MAC address. When the destination MAC address is not matching, they will ignore the packet. The packet touches those computers, but they don't process it further. They don't process the packet further because the layer 2 itself is not matching. This D computer will process it. Now assume it's a ICMP ping message. For ICMP, this PC, if it is receiving the packet, it's supposed to respond back. So the response packet will be sourced from DDD, and the destination to which it is responding is AAA. Now, when it checks the MAC address, okay, before checking the MAC address, when the frame hits the port F04, it learns the source. F04 is connected to DDD. DDD is connected to F04. It learns. Now, it checks for the destination MAC address in the MAC table. It is located in F01. So this time it will not broadcast. It will unicast. It will map it to the right port. So only it broadcasts if the destination is unknown. That's a very clever, smart device. Okay. It's not unnecessarily broadcasting. See, you saw here when a broadcast is done, this bandwidth of B, this link of C is unnecessarily consumed by the packet. The bandwidth is consumed. So always broadcasting is very bad. It's going to unnecessarily consume the bandwidth of unwanted destinations. So, of course, this is a smart device. It's not broadcasting all the time. Once it learns the MAC address, it does the unicast. All right. So listening makes this possible. Listening makes learning possible, and learning avoids broadcast. Fine. Now, very important thing here I'm going to say is, let us assume A is trying to talk to C now. A wants to talk to C. C. When this frame approaches, there is nothing to learn because it is already learned from the source. But when it looks for the destination CCC, it is a big question mark. Now, will it broadcast? Yes. Will the broadcast packet go to D? Will it go to D also? Because it has learned that F04 is in D. DDD is in F04. Will it go and search for CCC there? Very, 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 very correct. It will flag. It will use the common backbone which is We saw it, logical backbone. So even on the port where some MAC address is learned, it will flood. There is another reason for that. What if I have a switch here and earlier D was responding, and assume this C is connected here. So only when it floods, it will reach C. So even if one MAC address is learned, there may be many more MAC addresses on the same port if there is another device connected. For that, it has to broadcast. So it broadcasts to everyone, even on those ports which it has got some MAC address. Fine. Now, next thing is switches will do forwarding and filtering job. It will do forwarding and filtering job. When it will do forwarding, when it will do filtering. Let me show you another picture. I'll draw another picture like we have a switch, and we have another switch, and there's A device, B device, and I have CC device, EA device. And there is a link between these two. Now, let's say A is talking to C. This is D actually. A is talking to C. The MAC address of A will be learned on this F01. Now, if the switch do not know the destination it is going to flood, the flooding will go to all ports except from where it is coming. So the packet goes here as well as here. And C will respond, D will drop it. When it responds, and C responds back to A on F01, sorry, 2. On F02, CC is learned. And now, let us say B talks to C. B talks to C. Again, when this frame approaches F01, it learns another MAC address. So one thing what you see here is there can be more than one MAC address on a port. Now, because it wants to go to C, it knows already C, it is going to do what? Forwarding. Because it knows C, it will forward. Flooding it won't do, flooding only when the destination is unknown. It is now forwarding it to a particular port. Now what happened? A is now talking to B. For the first time, A is talking to B. If the switch do not know about B, assume, I want to consider this as a hub. If the hub never learns, hub always broadcasts, and A is talking to B, this packet will be flooded to this port as well as this port. The packet that goes to F01, what it will do, it will how and why? Because both the source and the destination are in the same port. So there is no point of forwarding it. It will filter. The switch has got nothing to do here. Why? Switch says A and B are in same port somewhere here. Down only. When packet is coming from down, why should I forward somewhere? There is no purpose of forwarding. So switch will simply drop it. It is not switch job to go back and say, hey, why did you send me? The destination is there. Oh, can't you see? Why are you sending me? It's not going to say that. It won't say that. It will simply drop here. It will simply filter. So because switches do these jobs, listening and learning, broadcast only in the destination is unknown, and then forwarding and filtering, switches considered as a smart device. Right. Now we need this type of smart device for every department. Each department is in one subnet. If I have only 5 people in a department and I have something like 10 departments like that, 10 department, 5 people in each department. Will you buy a separate switch for each department? No, you won't buy. Why is that? Why we won't buy? Because you got only 5 computers. For 5 computers, am I going to buy a 48 port switch or 96 port switch? But my company has already purchased like 48, 96, 300 port switches. No, you cannot waste the switches. Company has already purchased 248 port switch, let's say. 248 port switch company has already purchased. So you mean 96 ports totally, isn't it? Am I right? Yes, 96 port. Sorry, I lost you. And we got only 5 people in each department, and we got 10 departments. So totally you need only totally you have only 50 computers. And I already got 96 ports. Why should I buy more switches? Not necessary. No company will accept this. They will ask, hey, what is this you are doing? We got only 50 people and you are asking another switch. So we need to do something using this 2 switch. We need to provide dedicated switches for 10 departments. How can I give a dedicated switch for 10 departments? Am I a magician? How can I have 10 switches when I am given only 2 physical switches? I have given you a clue. How can I have 10 switches when I am given only 2 physical switches? How can I have 10 switches out of 2 physical switches? The physical is the clue. We are going to create virtual switches. That is what called as VLANs. Virtually, you are creating lands. Meaning what? Virtually, you are creating layer 2 domain. Can a member of one layer 2 talk to another member without router? Sorry, again I lost you.